Testing on YouTube. 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 Come on, why doesn't this go live? All right, there we go. Testing, testing. All right, there we go. Testing, testing. Let's adjust this camera so I can see the chat. All right, and I think we're also live on X. So let's go ahead and get started. Is this working? Feel like it's working. All right, I think we're just gonna go straight into it. Welcome everybody to another Who Post stream. We're going to be going over one of the more hype topics of the week. The stream is called Diffusion Game Engines, and this is going to be a review of this paper. Diffusion models are real-time game engines, sometimes also called the Game Engine paper. How's it going, Sagar? How's it going, Khalil? So yeah, this is the paper. It's got a lot of hype this week. There's a lot of different AI content creators which have been talking up this paper, which was recently released by Google on the 27th of August, 2024. But I want to be real with you guys. This paper is not that good. It really isn't. There's a couple other papers that I think are important when you're looking at this paper. There is this one here, Genie, Generative Interaction in Interactive Environments. This was also a Google paper published earlier this year, the 23rd of February. And we do actually have a stream on this one. And then we have the OG paper. This is published on 9th of May 2018. This is the Schmid-Huber World Models paper, which I think is basically the predecessor work for both of these. It's referenced in both of these papers. But yeah, just to cut to my opinion, I think both of these papers, World Models and the Genie paper, are better than this paper here, and I'm going to explain why, right? It's going to take me a while to explain, but I think this paper is a little bit overhyped. The Doom diffusion model renders faster than it did the first time I installed it on my 386 SX. Yeah, so Mark B there is referencing the fact that it does render faster than Doom in its original context. I think they mentioned that in this paper here. Let's see. Right here? I don't know if I can find it, but they did say that whenever the original developers were making this game way back in the day, they actually had it running at like less frames per second than even the... Damn, where can I find that? All right, whatever. All questions will be answered. But let's start with the abstract. We present Game Engine, obviously a play on the word game engines, right, where the gen there stands for generation, because this is a generative AI model. It's a game engine powered entirely by a neural model that enables real-time interaction. with a complex environment over long trajectories at high quality. And right off the bat, this sentence is exactly why I don't like this paper. Every single part of this sentence is over embellished, right? So game engine, this isn't a game engine. This is a world model that predicts the next frame, right? A game engine, I think, is something much more fully featured, right? When you think of something like a Unity or an Unreal Engine, I call those game engines, but those involve many more complicated pieces, and they can also simulate and create many, many, many different types of games, right? So Unity, there's a huge amount of different games you can create, and that's why it's called kind of the game engine, not just because it's the core part that runs the game, but it also allows you to create many different games. This is a hard-coded kind of overfit diffusion model that just generates the next frame in a sequence of frames. So this really isn't a game engine. This is more of a world model. Also, the word here, first, the first game engine, it's also not the first. There's literally another Google paper that is basically the same idea, and here's a 2018 Schmidt-Huber paper that's basically the same idea. So it's not a game engine. It's not the first version of this. It's also not really real-time. 20 frames per second, quite not real-time. You know, definitely very fast, but I wouldn't call that real-time. And then complex environment, not really a complex environment. Doom is really known to be the most simple kind of video game, and it's almost a meme that you can get Doom to run on like a toaster. So, and then long trajectories, also not very long. You know, we're taught, I think they say something like 3 seconds of context, and even then a single rollout isn't even particularly long. So yeah, not starting off well. And this is going to be my main negative opinion about this paper, is that it's kind of over embellished. It's not that what they did isn't impressive. There's in many ways in which it's a impressive paper, but just the amount of over embellishment and kind of like not quite right wording in this paper kind of left a bad taste in my mouth a little bit. How's it going? Yeah, Tharth, Sarah, and JJ Sheep. Is this project open source? I don't know if they open sourced any code. I think they just... Yeah, all they have is this github.io page with some stuff, and then they have the paper. There really isn't much to kind of open source here. At the end of the day, this is just Stable Diffusion 1.4. So they took a pre-trained Stable Diffusion model. Where is it? Right here. Yeah, this one. We need to run the UNet denoiser, which comes from Stable Diffusion 1.4, which is right here. So you can download this pre-trained model here. So Stable Diffusion 1.4 comes from V1.2, which is a fine-tuned version of V1.1, which is a diffusion model trained from scratch on Layon high resolution, which is a subset of Layon 2B. So this is really the OG model, then this is a fine-tune of that, and then this paper is a fine-tune of the, or not really a fine-tune, but it's a continuation of that. So there's one OSS related stuff I'll send. Okay. All right. Let's keep going. 20 frames per second on a single TPU, which is just Google's GPUs. Human raters are only slightly better than random at distinguishing short clips. Conditioning augmentations enable stable autoregressive generation over long trajectories. So the autoregressive generation means that it generates a frame, it appends that frame to the context of frames that it uses to generate the next frame, and then so on, right? So it's kind of very similar to a transformer language model in that it kind of produces the tokens one at a time, except in this case it's producing the frames one at a time based on previous frames. Doom has been run on kitchen appliances such as toasters and microwaves, a treadmill, a camera, an iPod, and within the game of Minecraft, just to name a few examples. And interactive world, a complex video game, the iconic game of Doom. So Doom is not a complicated video game, right? So they're kind of, you see here, you can't simultaneously say Doom is something that you can run on a toaster and then Doom is a complex video game. You know, I think those two statements are exclusive. One cool thing about Doom that I didn't realize until I saw this video. This is a Fireship. This is a YouTube channel I highly recommend just for the memes, but it uses this kind of 2.5D, so it actually isn't even a 3D game. It's a bunch of two-dimensional images or sprites that are kind of like warped in such a way to create this fake 3D environment, right? So it's not actually 3D, it's 2D. It's 2.5D, basically. And the other kind of important thing here is that every single part of the state is effectively on the screen, right? So there are games that are kind of like, for example, poker, where you don't know what the other hands in the other players have, right? You only know what your hand is, and you might know what cards are on the table. Then there's games like Go and chess, where you have 100% of the information if you can just see the board, right? All the information is there. Doom is a little bit more like Go and chess than it is like something like poker, right? If you actually look at Doom, you kind of know everything there is, right? The ammo count is on the screen, the health is on the screen, the armor is on the screen. So you kind of know the entire state of the game if you have a single screenshot, which is why it's not super impressive that you can effectively know the game state, right? That this model is capable of knowing the state of the game entirely within effectively a latent image, because the whole state of the game is written on the screen anyways. So, all right. Interactive world simulation conditioned on a stream of input actions and generates frames auto-regressively. What does conditioning on a stream of input actions means? It basically means that when you're playing this game, you are creating actions, right? That's the buttons that you click to perform some kind of action in the game. And then the game is creating frames, which are basically just images, right? So you have this paired data set of frames, which are images, and then actions, which are effectively just discrete, one out of a set of possible discrete actions. This denoising network here, which is the UNet, this is the stable diffusion model, right? This stable diffusion model, what it does is it generates images by iteratively denoising, right? So here we have an example showing you guys exactly what diffusion models do. Diffusion models basically start from noise, and then they iteratively remove that noise to get to the final image. And the number of steps you take here can vary, right? So you can do this in 10 steps and get higher quality images, do this in less steps and get slightly lower quality images. And the number of these diffusion denoising steps is kind of a bar, or is kind of a way to get the quality. So actually later on in this paper, they mention that they do specifically 4 DDIM sampling steps, which is how they're able to get this 20 frames per second. And then interestingly, they also try distilling it. So I think here, let's see, go to the distillation part. Where's the distillation? Simulation quality, context length, agent play. Where's the distillation? I thought I had this entire section here on distillation. Here we go. So they also try reducing the inference steps. So the main results are with 4 of these denoising steps. But one thing you can do with diffusion models is once you have a model that can get to a good quality in 10 steps, you can try to distill it down to less steps, right? So you basically try to get it to produce the same quality with fewer of these steps. So they try to go from 4 steps down to 1 step, right? And it actually still performs quite well. So even though it's 20 frames per second, they can really push it up to something like 50 frames per second or 30 frames per second just by reducing the quality bar a little bit. Okay. How's it going? Snooks and Ed. Previous work, Genie, wasn't open source either. This one. Yeah, I was trying to find if there was similar names, but there aren't any similar names. So with 2 of these papers that are so similar like this, I would have assumed that some of the names here overlap with some of the names here, but I couldn't actually, it seems like it's 2 completely separate groups of people. Right? Okay. Let's keep going here. Game and Gen compared to prior state-of-the-art simulations of Doom. And here they're saying, look at the world models paper, and then look at our paper. Look how much cleaner that is, right? But the world models paper that they're referencing here, this Schmidt-Huber paper, this is an old paper. This is a 2018 paper. They're using a VAE, variational autoencoder, that is a convnet. It's a small convnet, right? It's this vision model here, V, that compresses the game down to this latent space. And then the RNN, which is the controller, is playing effectively the latent space game rather than the full pixel space game. So that's kind of why I feel like this paper's way better than this paper, right? Because this paper actually gets the reinforcement learning agent, in this case, the policy is a recurrent neural network, to play using the world model. So they actually get an agent or a policy that is trained using this world model, versus in this paper, there's no policy that's taking that's using this world model in any way, right? At the end of the day, the reinforcement learning in this paper is simply used to collect a data set of frames and actions, and those are used to fine-tune a Stable Diffusion 1.4. So they're not wrong. Like, there's nothing incorrect about this, right? Their world model does produce higher quality images than the world model's paper, but it's producing higher quality images because you're using Stable Diffusion 1.4, right? It's not because these guys didn't know what they're doing. This is significantly smaller models, less compute. So, I don't know. State-wise Doom, in terms of hidden state, you could run quite complex games on a toaster. I guess the paper was speaking of complexity from two different perspectives. Yeah, I mean, in some ways, they're like, it is complex, but I don't think you could say it's a complex video game. I don't know. That's just my opinion. Okay, here they have some definitions here of some pretty standard things here. You got the latent states S, so these right here. So these frames, these blue squares right here, these are actual images. So you don't want to denoise on pure image space because that's going to take more memory and take more time. So usually what these diffusion models do is they actually run this denoising and this denoising process in a latent space. So you can see here, the first thing you would actually do is you would take your image and you would encode it into this little grainy little looking thumbnail thing, which is a latent representation of this image, right? So it kind of tells you what's in the image, but it's much lower dimensional, which means that adding and removing noise from it is going to be much faster and quicker, right? So these guys are basically doing the same thing, right? They're taking these frames and they're encoding it into this latent, and then the denoising network is iteratively adding noise to this latent during training, and then during inference it iteratively removes the noise from that latent, and when it comes all the way out the other end, right, this is what the next frame is supposed to be given all these encoded previous frames, and because you have the full rollout here, you know what that next frame is, so you can effectively just kind of do a standard little reconstruction loss there. Okay. They're also doing this cross attention here on using the action. So they're taking all the actions, right? They're embedding them. So it's not just a pure action like a one-hot, right? Where you're like, here's all the possible actions, and then this is the action that they took. You're turning that into some kind of embedding and then using that to condition. So similar to how in Stable Diffusion 1.4, what you're conditioning or doing cross-attention with in this UNet is something like text, right? So you're kind of removing the noise with a text that says an image of a cat, right? And that'll turn this thumbnail of noise here into a thumbnail that represents an image of a cat. Then you can feed that thumbnail into a decoder and get an image of a cat. In this case, what they're feeding into this cross-attention here is just the concatenated embedded actions. So ultimately, what this Stable Diffusion 1.4 is kind of doing is it's predicting the next frame in a latent space while being given the ability to attend to the embedded actions. Okay, the agent policy pi. This is almost irrelevant because the agent policy pi is what's taking actions here. So this agent here is some neural net that takes actions in the game, and then it receives rewards and observations back, right? But that policy pi is never really used in the actual world model, right? The policy pi is only used in as far as it is generating game environments, right? So here, they do it differently. In the Schmidt-Huber paper, they actually just use a random policy. So they're taking random actions in the game world, versus in this one, they have a little bit of an RL agent taking actions. And the real difference there is that if you have an RL agent and a policy taking actions in this game, you're going to be able to explore the game more, right? If you take random actions, you're not going to really explore a large chunk of the state space of the game versus state action space of the game, versus if you have RL with some curiosity kind of stuff, or some kind of like reward that encourages exploration, then you're going to be able to get a much better data set here of all possible corners and all possible actions that you can take in all possible states of the game. Okay. Simulation distribution function. Here you're trying to predict the next action or the next observation, O of n, right? So O of n given all previous O's, with all previous observations and all previous actions. So really, this is what you're trying to predict. You're saying, here's all the observations I've had up until now. Here's all the actions I've taken up until now. What is the next observation, right? So here's all the actions I've taken up until now. Here's all the observations I've taken until now. What is the next observation, this thing here? So that's basic input outputs. Okay. Simulated by autoregressively sampling observations. This is when you actually, quote unquote, play the game, right? What you're doing is you're just feeding in your action in there, and this unit here is fast enough to do this in 20 frames per second so you can get the observation out. That's how you're doing, actually playing the game like they're doing here. Okay. Let's keep going. In order to collect training data for this model with the teacher forcing objective, we first train a separate model to interact with the environment. These two models are trained in sequence. So they train two different things here. The first thing they train is this reinforcement learning agent. Again, the only purpose of this reinforcement learning agent is to collect a bunch of data, right? A bunch of paired frame action kind of rollouts, right? Here's a whole sequence of frames, a whole sequence of actions, so that they can fine-tune this diffusion world model. The policy pi, we design a simple reward function, which is only part of our method that is environment specific. Not quite, right? So another over. Look at this. Does this look like a simple reward function to you? So here's the reward function for the game of Doom that they came up with. It has 10 different parts, right? So this is what we call reward engineering in this industry, or reward shaping. This is when you have to design a reward function that allows your reinforcement learning agent to get better at this game and hopefully explore the game, right? Because really what you want here is to get every single nook and cranny of the game's state action space. So really what you really want to encourage here is exploration, not necessarily getting the highest possible score. But calling this a simple reward function, I don't think this is a simple reward function. This looks very engineered, right? So if you get hit, minus 100. If you die, minus 5,000. Item weapon pickup, 100. Secret found, 500. So you see this, so you get more points for finding a secret. That's going to encourage exploration. New area. Here you have some other hard, like L1 distance, how far away you are from the current situation, times 0.5, which is some magic number. 20, which is some magic number. 1 plus, which is some magic number. Look at this. Also some random arbitrary magic heuristic here. So I wouldn't call this a simple reward function, but okay. Record the agent's training trajectories throughout the entire training process, which includes different skill levels of play, right? As in the beginning, the policy is not going to be very good, so you're going to be largely kind of oversampling the start zone, but then the policy gets more and more advanced. It's going to start moving further and farther away from that start area, so the different skill levels of play is also going to change the kind of distribution of trajectories, right? So the hard trajectories are going to probably be more varied because the agent is able to venture out further into the game. All right. We repurposed a pre-trained text-to-image diffusion model, Stable Diffusion 1.4, which is a little bit older now, but this is the Stable Diffusion 1.4. You can actually just find it here on Hugging Face. Let's give that a little like. But you can scroll down here to the training, and they give you a little bit more information on exactly what this was trained on. So 256 by 256, Leon 5B English, which is captioned image. I guess that link is broken now. All right. We record. I think we already saw that. We condition the model F theta, so model F parameterized by theta. Trajectories T from T agent, so you're sampling trajectories from all the trajectories that were generated by your reinforcement learning process. On a sequence of previous actions and observations, so here's your previous actions and then previous observations, and you're trying to generate the next action, or the next observation. We simply learn an embedding a embed for each action, right? So rather than feeding in the action itself into this cross-attention, they're embedding it first. Just so I think you can reduce it, because rather than feeding all the actions, right, all possible previous actions, you kind of encode all of that into one latent, and then that's what you cross-attend to. Previous frames, encode them into latent space using an autoencoder phi, and then concatenate them in the latent channels. That's what's going on here, right? So they're encoding their observation frames, right? So they're turning the image and encoding it into this latent, and then they concatenate them, which basically just means they put a bunch of them like that in the depth dimension, and then that concatenated brick of latent observations is what's fed into the diffusion model. Diffusion loss with velocity parameterization. There's a noise schedule alpha bar T. So this is kind of pretty standard. I think this paper is actually the OG Stable Diffusion paper. We corrupt context frames by adding a varying amount of Gaussian noise to encoded frames in training time while providing the noise level as input to the model. So they do a little bit of data augmentation here, where in this part here, where they're encoding these frames and then using these as input to the denoising network, they take these frames and they don't just feed them in as is. What they'll take is they'll actually add some Gaussian noise to those so that the model is capable of dealing with noisy latents, right? Because one of the things that you're going to run into with this type of autoregressive generation is that if you have a little bit of error that gets introduced, it's kind of slowly starts corrupting everything, and you kind of get this, once you're off the training distribution, then it's going to be kind of shitty, right? And that's kind of what they're showing you here. So start here, you're using this to auto-regressively generate the next frame and the next frame and the next frame and the next frame. You see how it kind of gets increasingly more deep fried. If you add the noise augmentation, where you're putting noise into those latents when you're training the diffusion model, then the diffusion model is capable of dealing with noisy latents and you don't get that drift. But this is pretty standard. I feel like everyone kind of does that, right? I think these guys also put noise. These guys also put noise. So that's not even really an original idea there. And, okay. Let's see what else. Past observations and past actions. During inference, we need to run both the UNet denoiser and the autoencoder. So they need to run this part here, the encoder, right? Because they need to encode every single frame, and they also need to decode every single frame. So they need to run this the encoder and the decoder every single frame. And they also need to run the denoiser, which is this part here, right? The actual UNet that iteratively removes that. And they need to run that however many times they're doing this, right? So they're doing it 4 times. So they need to run the encoder and the decoder once, and then they need to run this 4 times. So that's all of that needs to happen for one inference step. A single denoiser step and an evaluation of the autoencoder both takes around 10 milliseconds. And with only 4 DDIM sampling steps, we observe no degradation in simulation quality when using 4 steps versus 20 steps. So you can see that 20 steps would be just so much longer, right? Imagine 20 steps of this versus just 4 steps of that. 4 denoising steps leads to a total UNet cost of 40 milliseconds and the total inference cost of 50 milliseconds, or 20 frames per second. Okay. How's it going? They call me Ken and Ogum the Bold. I used AI to feed a tribunal appeal ECHR legal argument against starvation sanctions. I have no idea what that means. Ogum. All right. Agent model is trained using PPO with a simple CNN. So PPO, proximal policy optimization. This is quite old at this point. So it's kind of the most basic reinforcement learning policy you could train. But again, it doesn't really matter because they're not trying to get this RL agent to be very, very good at the game of Doom, right? They're not trying to beat some kind of Doom benchmark. They're really trying to get it to explore the state action space of Doom. So that makes sense, but it would have been way cooler if they did what this paper did, right? So in this paper, they actually got a smaller controller model, aka the policy, to learn to perform a task using the world model. So in the original Schmidt-Huber paper, not only do they train a world model, but then they also get a policy to perform actions in that world model, right? To use the world model to learn, versus here, they're using the RL agent just collects data. Right? I feel like it would have been so much cooler if they then took this world model and then got an RL agent to learn how to play Doom in this world model. That would have been the cool part, but they didn't do that. And part of the reason you can't do that is because this world model here does not give you the type of explicit game state that you need to do this type of RL training here, right? This policy, this PPO policy that they're training here, it's only capable of learning because it has all this information, right? Health delta, armor delta, secret found, new area. Like, you can query a real running version of Doom and get all the different things you need to calculate this reward to train this policy. But you can't do that with this, right? There's no explicit enemy health or ammo amount or any of that. So even though this is a world model, it's a world model that doesn't give you the state information required to even give the reward that you would need to train a policy on it. So the most that you can do with this world model is just kind of sit around and like kind of play with it as a human, right? But I don't know. Okay. Simple CNN as the feature network. It's fine. It's not super important. They unfreeze all the UNet parameters. So sometimes when you're fine-tuning these models, you'll only push gradients into a subset of the model parameters, right? So maybe you'll only push gradients into some of the layers into this UNet, or maybe not into the encoder decoder. Here they're actually pushing gradients into all parts of this Stable Diffusion 1.4. And combined with some of the other information here, right? So they say they train using 128 TPU v5e. The TPU v5es are the latest TPUs, so 128 of these, 700,000 training steps, over 900 million frames for training at 320 by 240. This is an insane amount of compute. So really, when I read this paper, this is overfit hard, right? So yeah, the quality is very nice, but it's because you're overfitting the shit out of a Stable Diffusion model with a huge amount of data, right? That's kind of ultimately how they're able to get that quality, is because they have a huge amount of model capacity. They're pushing gradients into the entire UNet. This UNet is effective. This Stable Diffusion model is now effectively worthless except for the game of Doom. It really only can do Doom at this point, and every single parameter has been turned into helping this objective of creating Doom images. And 900 million frames is a huge amount of training data, right? And this is actually an opinion that Dr. Jim Fan also shares. So Game Engine overfits to the extreme on a single game by training on 0.9 B frames, right? 900 million is 0.9 B. If you actually look at the original Stable Diffusion, this is only trained on 2B. So 2B, it's like half the size of the training data set for the original Stable Diffusion, except it's only the game of Doom. This is a huge number. Almost 40% of the dataset used to train Stable Diffusion v1. At this point, it's likely just memorizing how Doom renders from every corner of the game in all scenarios. Doom doesn't have that much content anyways. Game Engine is more like a glorified nerf than a video gen model. I agree with these takes. I agree with Jim Fan here. This is just an overfit Stable Diffusion on a game, and like they didn't even do the cool shit that we found in some of these other papers, right? So Genie, which is another kind of world model paper that we read earlier in the year, this one had a very cool part, which is that you can create new games. So you can basically go from a text prompt into a game. So it's a lot of different games. And they also had this part in here where they're learning these actions, right? So it's basically they're learning actions, latent actions, like the actions themselves can kind of be learned from the game itself. So, for example, here they can feed it a video of a robot picking up a thing, and they kind of eventually learn what the down and what the up and what the... So they almost like learn the action space of the game as part of the training process, versus here, the action space of the game is hard-coded specifically for Doom, right? Which, again, kind of conflicts with part of what they're saying here, right? Where they're saying the only part of our method that is environment specific. Not quite, right? Your action space here is environment specific. So, yeah, not looking particularly good. Let's keep going here. To be or not to be, that's the game. That's a pretty good little quip there. Generation quality improves with the length of the context. We quickly approach an asymptote, and further increasing the context size provides only small improvements in quality. The model has over 3 seconds of history. And I think the reason that this doesn't matter is because the full game state isn't 1 frame. So this is kind of what I was saying before, but in this game of Doom, like, this is the entire game is written on the screen, right? I don't actually know because I haven't really played Doom, but like, is there something in the game where it's not written in the screen and then you could go back and see it, right? Like, is there maybe the concept of like opening doors or like opening a chest or like grabbing an item or something like that? Because those would be parts of the game that are not available in this little instantaneous frame, right? But what they're saying here with like, hey, we tried with just 1 frame where we just give it the most current frame and it's able to get the next frame. The reason that works well is because Doom is a very simple game and the full game state is effectively on that 1 frame. So that's what that tells me. They evaluate with PSNR and LPIPs. These are metrics that are generally used to look at image quality generation, but the image quality is not really an important part of world models, right? This is kind of where I feel like they're not focusing on the right things here, right? Like the cool part about the world model Schmidt-Huber paper is that the reinforcement learning agent is operating inside effectively this world model version of the game, right? So the RL agent only sees this Z, right? It only sees this Z, which is a latent version of the current frame, and then it has this H, which is the hidden state that it's getting passed to recurrently from the previous compute step, right? So every single step, it gets this H and it gets this Z. That H and that Z are very compressed, right? Because the H is limited in size, and in this RNN step, you're basically taking all the new information and trying to pack it into that H. So the fact that you can get this quality from something that is being compressed and then being lossily kind of moved with the H and the Z is much more impressive than something like this, where, yeah, you're generating a very high quality frame, but you are literally encoding the entire rollout, right? You're encoding like 10 different frames, 3 seconds at 20 frames per second. What did they say exactly? Like 60 frames and 60 previous observations, or 60 previous observations and then 60 previous actions, and then using a Stable Diffusion 1.4 model that has been overfit to shit on this Doom engine, or on this Doom data. So is it really that impressive that you're capable of generating a super high quality image? Not really. So is using PSNR and LPIPs, which are really just about the quality of the image, is that proving that you're state of the art? No, it's just proving that you use Stable Diffusion 1.4 and overfit the shit out of this entire problem. So I just don't feel like this is the right metric to focus on for a world model paper. Sorry, I'm being kind of negative, guys. Enemy locations, list of weapons. Any idea what this would look like if it wasn't overfit? Do you think there would be differences? Yeah, I would love to see what this looks like if you don't use a giant Stable Diffusion, or if you just train this Stable Diffusion from scratch, right? Because the fact that they used a pre-trained checkpoint, that's also, you're also getting a lot of intelligence from that, right? There's a lot of intelligence in this Stable Diffusion v1.4 checkpoint that you're using effectively to transfer learn into this task. So if they had done this from scratch with a diffusion model that was much smaller, that would be more impressive. What would you consider positives for further development? Okay, what are the positives of this paper? I don't know. You know, like, to be honest, like, the positives of this paper is just that it's Doom. You know, like, if you want to think about papers as ultimately the most important metric for a paper is citations and kind of virality, right? You want your papers to be published everywhere. So whenever they decided to do this paper, picking the game of Doom, right, was a very, very intelligent idea. So that is really the best idea of this paper, is like, hey, there seems to be this entire gaming community that is really obsessed with Doom running on toasters, and like, people have been into this game for so long. What if we could take some of that hype, right? So they basically were like, what can we do with AI to create and use the fact that Doom is kind of popular, and we can piggyback off that hype train in order to get a lot more eyes on our paper. And you know, they did it correctly, because if you really look at it, like, there's so many people just talking about this paper, right? Comparatively, less people talked about this paper because it, you know, wasn't about Doom. It's just about made-up video games. But this paper is so much more intricate and involved and interesting. And same with this paper, right? Not just because it's old in 2018, but just like I said, the fact that the RL plays inside the world model, that's pretty fucking cool. If they could get an RL agent to play inside this world model, that would have been a good thing to show. But they didn't show that, right? Because the only way they could get an RL agent to get good at Doom was by using all this explicit information, which they don't have access to in their world model. Let me see. Generative GTA transformer. I think the point of this paper is to demonstrate that it can be used to generate video games of the future, and that's why people are excited. Yeah, I mean, so when you think about, okay, what is this paper really showing you? I think it's kind of showing you what Andre was writing here, right? So this is Andre, 100% fully software 2.0 computer, just a single neural net and no classic software at all. Device inputs directly feed into a neural net. The outputs of it directly display as audio video on the speaker screen. Can it run Doom? It can probably very close to simulate Doom if you ask nicely. So here's Andre basically predicting this fucking paper. But, okay, why is this potentially great? So this could be great because let's say you have a game like Crysis or like GTA, right? Generating frames of GTA, right? Like actually running GTA requires a lot of compute, right? You have to be doing all this physical rendering. You have all these meshes. You have this scene. There's objects moving. There's animations playing in there. There's lighting. There's the lighting interacting with different things. You have all these different materials with different properties. So there's a lot of compute that goes into calculating the appearance of every single frame in a game, right? So if you can just get a neural net to output the frames one by one that in a way like this where you can interact with it, then now you could probably run this ideally with less compute, right? So you can just take this network here and whatever the cost of inference is for this network, that's all you need to play this game. But I kind of disagree with that because the whole point of Doom, right, was that Doom was kind of designed very meticulously with this weird kind of like 2.5D magic, right, so that it was extremely efficient. So Doom itself can run on a toaster because the game has been designed to be extremely efficient to figure out what is every single little frame going to look like, right? So that's why you can run it on a toaster. So if the whole argument is that, hey, we can run games cheaper because we can now use a neural net rather than using all this kind of hard-coded code that somebody wrote and had to design, how does that work when the compute required to run Stable Diffusion 1.4 is probably almost guaranteed that is more compute and more parameters and more overhead than literally just running Doom, right? So, you know, if you would have done this with GTA and then you say, okay, this world model here is significantly cheaper to run than actual GTA, that would be impressive. But right now, you're just showing me that a very, very large overfit network, which is more compute intensive than the original Doom, is capable of running Doom. Okay. And also, another kind of point on that, right, is that you can't... This is not, like, controllable, right? Like, there's nothing that you can really control here, right? Versus a real game engine, the whole point of a game engine is that you can create games how you want them, right? You can say, okay, I want a tree here and I want a tree there, and on this part I want the death animation to be this, right? So the whole point of a game engine is to allow you to create a game, and granted, it's a very complicated process, but you can't do that with this, right? This is just a hard-coded thing that only generates frames for this Doom game, and it's only possible to do that if you already have that game in such a way that you can train or generate 900 million frames of it. So it's like you need the game to create the data to create this world model to simulate the game. So you know you don't get it for free. AI just emulates a machine that runs Doom. It will always be slower than running it directly. I don't know 100%, right? So Frigo, that's the kind of the point that I'm making, that hey, the AI that is emulating the game is more compute than the game itself, right? It's way over parameterized. So that's why it's not that impressive, but if there, you could do that, right? You could conceive of a paper that's similar to this, where hey, they end up showing you that this model that they use here is less compute than Doom. That would have been fucking crazy if they showed a very, very tiny little multi-layer perceptron that can do this type of shit. and it runs in a lower compute budget than the original Doom, that would have been like best paper of the year. That would have been fucking insane, but it's not, right? This is a big ass diffusion model that's been pre-trained on 2 billion images, and then they train it on another 900 million images. IDK. Let me see. You guys are... I feel like I'm being a little bit negative, and I apologize, but on the other side, it's you guys are kind of like fighting back, you know? I like it. I like this kind of discussion that we have going on here. Other world models paper relate more to training robots and RL. Yeah, I mean, that's kind of where, for example, Jim Fan here, he makes a point on this as well. He's like, what's an example of a truly useful neural world model? Elon Musk said in a reply, Tesla can do something similar with real world video. Autopilot team likely has trillions of steering wheel action pairs, blah, blah, blah. So it is entirely possible to learn a general driving sim that covers all kinds of edge cases and verify new FSD. So that's really the usefulness of this kind of world model paper, right? The whole point of creating a world model, right, is in order to train an RL agent in that world model, right? Because that's really what Schmidt-Huber does in this paper, and that seems like the purpose of this, right? It's like you learn this world models because executing actions and training a reinforcement learning agent in a world model is supposed to be cheaper than the real world, right? So if you could train autonomous vehicles inside this world model, now we're talking. Now there's some usefulness there, but they're not doing that here, right? You're not training anything on this. Any chance of this being used for synthetic data generation for a game? Yeah, but I mean, you don't like why would you use this to generate Doom images when you literally have a data set of 900 million Doom images here? It's like a chicken and an egg. It's like they're presenting to you a chicken and they're like, holy shit, dude, we can make an egg out of this. But it's like, yeah, the chicken came from an egg. You already had an egg. I can imagine AI being faster for some heavily ray-traced and path-traced games, but definitely not for something as simple as Doom. Yeah, that would have been more impressive, right? Again, I'm saying it's like the fact that it's Doom is part of the problem, right? So picking Doom was a great choice because you got this virality, right? Like just look how much pop they got from this, right? Like there's so many people making videos. I'm fucking making a video about this, right? So like they succeeded by picking Doom as the thing in order to get virality, but it's just that Doom is literally the world's simplest video game. Not actually, but that's kind of what it's like. There's a reason people can run it on toasters. So overfitting on Doom and then not even using that for any other purpose other than just showing you that the images that come out are good. You know, like think about it this a different way. Imagine if there was a paper where someone took Stable Diffusion v1.4 and generated and then collected a data set of 1 billion cat images and then fine-tuned Stable Diffusion 1.4 on 1 billion cat images, and then they said, look at how good our cat images are compared to other people's cat images. Would that be impressive? Not really, right? I would just be like, okay, that's cool. Thanks for the 1 billion cat images. I guess if I ever want to generate cat images, I can just use your data set of 1 billion cat images, right? So it's the same thing here. It's like we generated 900 million frames of Doom, and then we overfit a diffusion model to just output Doom frames. Cool. You know? It's almost like every single next frame prediction that comes out of here is probably in here, right? I wonder how many unique states of Doom there are. Like, if they did a reverse image lookup, like if they looked at the next frame prediction and looked at the data set here, would every single frame that gets predicted effectively be in the data set? Right? Is it actually extrapolating at all? Does it generate a directional stereo soundstage? I don't think there's any audio in here. This is just images, and then it doesn't even do any actions, right? That's kind of the cooler part of the Genie paper, is that the actions are also like they have a more interesting use of the actions here, right? Where they basically discover the actions. Here, the actions are hard-coded, and there's no actions coming out, so you have to provide the action, or you could use a policy to provide the action. Why didn't they do that? It seems like such an easy thing to do that I'm wondering whether they did it and then they just didn't get the results they wanted and they didn't talk about it, right? Because you could just take this agent here, this pre-trained agent, which they trained in this game environment, and run that agent policy on this world model, right? What happens if you do that? What happens if you run this agent on this world model? Does it actually work or does it not work, right? Because if it works, then show that and then put it on here and then it'll be great, you know? People would love it. But like the fact that they didn't do that, or they did it and they didn't show it, means that maybe it didn't work, right? Maybe this policy here that's interacting in this game, it is a little bit overfit in itself, and if you use generated frames rather than real frames, it doesn't work, right? There's little things like that that can mess with it. Minecraft would be perfect as a target game. The open worldness and randomness would solve these problems. Yeah, Minecraft would be another interesting game to do here, and it's, I think in terms of like the visual quality of the game, I feel like Minecraft is maybe just a little bit better than Doom. But the interesting thing about Minecraft is that the game is a lot more exploration based, right? So if you were to just have a random actions, I think here, for example, let's do random actions. Let me see if I can find the part here in the Schmidt-Huber paper. Right here. Are you here? Trying to find the random action part, but here they use a random action to generate or effectively explore the state action space. Here they're using an RL agent to explore the state action space, because the RL agent over time will discover more and more of the state action space. But I think the game of Doom itself doesn't have a huge state action space, right? How many rooms and possible things are there in the game of Doom? I feel like if you play the game of Doom for 10 minutes, you kind of run into every single enemy, every single gun, every single room. I don't know 100%. Again, I'm not like an actual Doom gamer, but Minecraft is going to be way more complicated than that, right? If you run this loop in Minecraft, this data set here is probably not going to include all possible things you can do in Minecraft. So whenever you feed it some new thing that you're doing in Minecraft, this stable diffusion here would probably not be able to generate the next frame, because this RL agent was not capable of exploring the entire game, right? So I think they just really needed to connect these together. That's really what I feel like this paper is missing, is some kind of connection here where once you train this world model, you use this world model to train the RL agent, and then you can show that the RL agent is working better in the game, right? So like connect these two parts, right? That's really what this is missing. Hupo, do I have some small compute ideas? I do have small compute ideas. I'm currently trying to work on a little AGX Orin. Here, let me pull it. This is my little edge compute setup. I have a battery, and I have an AGX Orin, which is probably the best edge compute you can get right now. It's been a while. I think they're going to release a new one relatively soon here, but I'm running it right now to see how long it'll last on this battery. But I don't know. I feel like limited compute, it's all about the edge. You know, it's all about like, how do you make inference faster? Can you actually do training on the edge? I think that's something interesting to think about, right? Like, but yeah, unfortunately, lots of the ideas work if you have big compute, right? this paper is really only possible because of the big compute. If they didn't have big Google compute, they would have never gotten this type of result. And if they didn't get that type of result, it probably wouldn't have been that popular because there really isn't that much else to this. Real-time learning. Yeah, some kind of like continual learning, lifelong learning, sometimes also called federated learning. Federated learning is a little bit different, though. That's when you like kind of have a bunch of machines that are calculated gradients and they all kind of push them back and then you kind of distribute. So I'm thinking more like some kind of device that trains a model that it runs itself. So it's kind of like completely isolated from all other devices and all other training. Kind of alternating between training and running inference. I don't know. I have some ideas, but not yet. It'll be forced to extrapolate on Minecraft, right? Yeah, that's kind of what I was saying, is that in Minecraft, you're never going to be able to get a data set that is effectively all possible state action tuples of Minecraft. So this world model would have to extrapolate, versus in a game like Doom, 900 million is probably every single possible situation you could be in the game of Doom. So this world model here is never going to have to extrapolate. It's just kind of interpolating. Would it be possible to use a diffusion model for real-time Gaussian splatting generation for interactive multiplayer 3D VR? That's a lot of different terms there. I think eventually, yes. Eventually, I feel like some kind of interactive VR video game that is being generated frame by frame by a neural net, like that's actually I kind of agree with Karpathy on that, right? Where when I think about the limited compute of a VR headset, right, are we going to be running like an actual rendering pipeline on that VR headset, you know, that's actually doing light bounces and all of that shit? Or are we going to be running some tiny little multi-layer perceptron that can run hundreds of times a second and generates the next frame that is being rendered on your VR headset? I think that's where we're moving. So I think directionally, this paper is kind of sneak peeking the future of like, hey, we're not going to be using these Unity and Unreal game engines anymore. We're going to have these neural nets that effectively generate the game as you go. I think that is correct, right? And that's the same thing that we saw in this Genie paper, right? Like, it's the right idea of like, hey, let's use world models to basically as the next generation of gaming technology, but we're just not really there yet. I'm trying to scroll through. I feel like I missed some of your guys' questions. They should attempt to train the model on ultra-realistic game. I think I talked about that. Pokemon would be better. That would have been another good idea, right? So I think there was also another one. There was like a RL plays Pokemon. Yeah, look at this guy. Training RL to play Pokemon with, look at this, over 6.7 million views. That's really what I'm learning here, is that in today's kind of like super accelerated kind of social media world, you can't just publish fucking papers like this, right? Like that don't really like, you got to have something. It's got to be like, it's got to have like a nostalgic kind of hook, like, hey, Pokemon, right? Like this guy literally this is PPO on Pokemon as far as I understand. Right? It's just fucking Windows setup guide, like PPO on Pokemon entirely in Python, 7K stars, 6.7 million views, right? Like fine-tuning a stable diffusion model on 900 million frames of Doom, and everybody's all over it, right? So it's like, it's almost like the actual novelty or like ideas within the research paper don't even really matter anymore. You just have to have your pulse. You have to have your finger on the pulse of society and understand what is it that the people want to see, right? And the people want to see Doom. They want to see Pokemon. So that's just the world we're in. what would the result be if we use this model for a very similar Doom-like game or something like that? It probably wouldn't work. I think this is very overfit. I don't know, right? I don't actually have the model. They didn't release it, so we can never really check. But I suspect that if you started feeding in frames from, like, I don't know, Pokemon, right? It would basically just look like trash. It wouldn't. It would kind of look like this, right? It would almost like dissipate immediately. Within the first couple frames, it would just become some garbage. And then as soon as you're outside of the distribution of training, then it's basically impossible to come back. Okay. Is there anything else? What else do I have here? I have the original Schmidt-Huber paper. Here we go. Here's a quote from the OG Schmidt-Huber paper. We can take advantage of deep learning frameworks to accelerate our world model simulations using GPUs in a distributed environment. The benefit of implementing the world model as a fully differentiable recurrent computational graph also means that we may be able to train our agents in the dream directly. This is the whole point. This is what we're going towards. Train embodied agents in the dream directly, right? Use the dream to train the RL, right? Learn general driving in the dream, right? Versus here, you're not doing anything with the dream. You just create the world model or the dream, and then you just kind of, that's it. But you want to use the RL in the dream. That's the whole point. That's the magic. I hope future supercomputers will be capable of extracting weight gradients from the current checkpoints, improve them, and convert them into whatever AI technology we use in the future. I don't exactly know what that means, but I love the enthusiasm. The choice of using a VAE for the V model and training it as a standalone model also has its limitations, since it may encode parts of the observation that are not relevant to a task. After all, unsupervised learning can not, by definition, know what will be useful for the task at hand. So, kind of what they're saying here, right, is that in the Schmidt-Huber paper, when they were training this VAE to effectively compress the game of Doom into this little Z, right? This little Z so that you can run your reinforcement learning on this Z, which is cheaper, right? The problem is that that VAE is effectively just trained to reconstruct the observation. So it doesn't know what's important and what's not important. It's kind of treating all the pixels kind of equally, right? It's just trying to reconstruct it in the highest quality. So here, there's kind of a similar-ish effect, I suppose. I guess you also have the actions here, so maybe this is a little bit better because you can condition this on the actions, right? But unless you have the RL in the loop here and the RL is pushing gradients into this that force this diffusion world model to actually focus on the things that are important for beating the game, right? This is only focusing on the things that are important for recreating the next frame, right? So really this diffusion world model just wants to make the cleanest possible thing. It wants to make screenshots of Doom that are basically virtually indistinguishable from Doom. But that might not be what you want out of a world model, right? What you want out of a world model might be something a little bit more nuanced, because you don't want it to necessarily just generate the highest fidelity images. You want it to generate, like, compress the world in such a way that it's focusing on the important things, right? So maybe here in Doom, right, in order to beat the game of Doom, you probably have to kill the enemies. You have to, like, know where the enemies are, right? So you don't really care about the wall color of Doom at all, right? You don't really care about the sky color of Doom at all, right? Because if I didn't tell you what the wall texture was, you could still get superhuman performance on Doom. But in this world model, there's a lot of energy that's going into reconstructing the exact wall texture, right? So there's a difference here. This world model is really just trying to recreate every frame of Dune perfectly, or Doom perfectly. I don't know why I keep calling it Dune. But in a world model, especially if you're going to be using your world model to train a thing, right? If you're using your world model to train the agent in the dream, you almost want it to kind of hallucinate the wall texture. You know, you want it to hallucinate the floor texture, because those things don't really matter. Maybe we will see. All right, what else, guys? What else? I think we got pretty much everything here. 20 frames per second. The model only has access to a little over 3 seconds, so it's remarkable that much of the game logic is persisted for drastically longer time horizons. While some of the game state is persisted through screen pixels, they're aware, right? They're like aware. This is what I was saying. It's like the whole game is on the fucking screen, right? It's like, here's the entire game state. That's pretty much it. The health, everything. It's like, wow, it can keep track of health. How is it keeping track of health? It's because it's written on the fucking image. Starting with crap dreams is a really good proof of concept. I don't know if you want bad dreams, but there are games like Cyberpunk where the game is 100 gigabyte stable diffusion, is much smaller. Imagine using these for those type of games. Yeah, that would be super interesting, right? Like, that's what what I'm saying is, if you take the game of Doom and you say, how big is Doom? How big is Doom megabytes? It's 2.39 megabytes. Stable diffusion 1.4 size. I think we have it here. We can try to download it. It's Unet. Look at this. 3.4 gigabytes. 2.39 megabytes. I rest my case. You used 3.4 gigabytes to compress 2.39 megabytes. We don't dream in HD exactly. Yeah, Tharth, you're almost getting like more. I actually think that there's something going on in the brain, right? So like this is kind of taking a step away from this paper and kind of more talking about world models in general, but the human brain has a kind of a world model, right? Like, I think Schmidt-Huber explores this in the beginning, right? But like, as a human, one way of understanding the predictive model inside of our brain is that it might not just be about predicting the future, but predicting future sensory data given our current motor actions, right? So I think what happens when you're dreaming is that your world model in your brain is being used to create training data for you, right? So you can't, if you think of every single little human as a reinforcement learning agent, right? You can't collect experience 24/7, right? Because 50% of the time it's dark outside and you can't see shit. So you can't learn anything new because it's too dark to see anything, because we're vision-based animals, right? So evolution comes up with a nice little handy trick of, hey, let's do our learning in dreams. So let's take that world model that we have in our head, and whenever it's dark outside, just lay on the ground, close your eyes, and play your world model in your head. So that whereas animals that don't have this REM sleep, they only get to train and learn during their waking windows. If you have REM sleep and you have dreams, you can now train during your waking windows, and your sleeping windows, right? So I think that's what dreams really are. They're basically simulated training for yourself. And if you actually look at some of the smartest people that have ever existed, they actually learned how to make use of this. So I don't know if you guys are into lucid dreaming at all, but lucid dreaming is whenever you can kind of gain consciousness or lucidity in your dream and you can control it, right? And I've spent a lot of time trying to get good at this, and I'm definitely not very good at lucid dreaming, but when I've lucid dreamed, I kind of just fuck around. You know, I remember one lucid dream where I sat there and I spawned a giant like robotic exoskeleton, and I was just like fucking running around in my robotic exoskeleton, and I was like, that's pretty fucking cool, right? But you don't need to do that, right? You can use your lucid dreams as extra training time. And I think Tesla did this, and also the guy at Intel who's like a system design guy, he's like older now, but he said this exact same thing too, where he uses his dreams to do more engineering, right? Like one quote from Tesla is that in his dreams, he would build his machines. So while everybody else is sleeping, he's sitting there in his dreams grinding, right? So if you can learn how to lucid dream and you can learn how to effectively learn in your dreams, you can work 20-hour days. Everybody else is working 16-hour days maximum, right? Because they have to sleep. But if you can learn how to use your lucid dreams to get better at something that helps you in the real world, now you have almost twice as much training time as other people. So this is a pattern. This is why I kind of almost got into lucid dreams, because I wanted to get good enough at lucid dreaming that I could do that kind of stuff. But it's fucking hard, right? And the idea of like having enough lucidity to like actually like study machine learning in my dreams, that's a little bit too much for my brain. What are the arguments against work on world models? I've had people say they're not valuable because it's extremely difficult to simulate things like laminar flow or movement of water. I don't think it's bad to work on world models. I think it's a very promising research direction. You know, I think that all of these papers are good. I just think these two papers are better. I just think the world models and the Genie are better papers than this one. But I wouldn't say it's like a bad paper. You know, it's not really showing me anything new, right? All they did is they just overfit a diffusion model to Doom, and that's pretty much it. Like, they didn't really do any... they didn't use it for training like they did in this one. They didn't do the kind of latent action space that is discovered like they did in this one. So there's no, it's just like steak with ketchup, you know? Staring at hard work, you basically realize that in the dream, you're dreaming when you look at your own hands. Staring at hands. Yeah, that's actually a very good trick. That's the one that I learned. So basically, the way that you can lucid dream is you have to establish a habit that will occur in your dreams, right? So if you have some kind of habit, such as maybe touching your ear, in your dream, you will do that habit. You will touch your ear. So the main trick is to learn some kind of habit. So the one that people focus on is, for example, you rub your hands together. So occasionally during the course of the day, remind yourself like, oh shit, rub your hands together, and then think to yourself and be like, am I in a dream? And then rub your hands together, and then think, am I in a dream? And then think to yourself and be like, oh, I'm not in a dream. This is real life. And if you start doing that enough times during the day, once when you're dreaming, you'll do that. So in your dream, you'll start rubbing your hands together and you'll think, am I in a dream? And then suddenly you'll come to the realization of, holy shit, I am in a dream. And then boom, there you go. Now you've achieved lucidity. And there's other versions of these. Like some people have like doorways. So like every time you go through a doorway in the real world, remind yourself, am I dreaming? But basically all of them boil down to this core principle of like reminding yourself that you're in a dream or not in a dream, and then taking that habit and getting it to trigger inside your dream. The point of dreams is to generate synthetic data. Yeah, I mean, that's kind of my argument, is that dreams are effectively like training inside a world model in your head. Literally jailbreaking our own world model. Okay. I don't know what else, guys. I feel like I pretty much ran through this paper. There isn't much to it. Here's more information on the Genie paper. You can see it's a little bit smaller, 200M parameters, 300M. $256 TPU v5s. 125K steps. These guys use 700K steps on 128 TPU v5es. What's the difference between v5es and v5ps? V5e versus v5p TPU. Here we go. A v5e has 256 chips per pod. A v5p has almost 9,000 chips per pod. V5e has way lower flops, less memory. So actually, which one of these is more compute? 256 TPU v5ps. Damn, so they actually did that on a smaller compute bit. 128 v5es is basically just half of this cluster here. So actually, the Genie paper used more compute. I guess 125K steps with 700K steps. And also, these guys are training with a batch size of 128 versus here, the batch size is 512. But here, I think the image size is also smaller. What's the image size here? 160 by 90 versus here it's 320 by 240. It's very hard to compare, right? So it's like, which one of these actually used more compute? I don't really even know, to be honest. Similar-ish compute. So E is eco, and then P is for power. Is that what it stands for? V5 economy, and then V5 premium. Economy and pro. Yeah, I'm just guessing too. Depending on stimulation, NMDA receptors can lead to either long-term potentiation or long-term depression. Those correspond to real data and fake data phase of the forward algorithm. I don't know. Shep, both used a lot, not gonna lie. Yeah. I think that's the TLDR, right? Is that like these Google papers, this is also a Google paper, like these guys have insane amounts of compute, you know, like some random dude with the Genie paper is using 256 TPUs. If you actually look at the Schmidt-Huber paper, like, what are we talking about here? It's probably just like one GPU. Let me see if I can find it. Training each model required less than an hour of computation on a single GPU. Yeah, so like, you know what I'm saying, when they do this thing here, they're like, wow, like look how much better we are. It's like, motherfucker, 1 hour of computation on a single GPU versus 900,000 or 700,000 steps on 128 TPU v5es at 320 by 240. Like, that's not impressive. You know what I'm saying? It's like going to a toddler and like lifting a 100-pound weight in front of a toddler and being like, oh, I'm so much stronger than you. And the SD 1.4 checkpoint used more compute than Genie as well, right? So that's a very good point by Heups as well, is that they start from the pre-trained checkpoint of Stable Diffusion 1.4. So they're already starting from something that has been trained already. You know, they're starting from this, which has already been trained for 194,000 steps on Leon, and also fine-tuned on another 225,000 steps versus I think this one is from scratch. I don't actually know. Is this entirely from scratch or is this using a pre-trained model? I don't remember anymore. Video tokenizer. Mask GT. Let's search up scratch. What about pre-trained? What about pre-train? No. Okay, so I don't know if the Genie one is pre-trained or not, but it could be. If not, then yes, this one has used way more compute over the lifetime. Lava architecture versus other vision capable. Look at their diagram. You're talking about in here? I think the confusing thing here is that they also do it with different ones. So in the Genie paper, they have the robotic one, and then they have the kind of like side scroller one. So I think there's a couple different models here. Maybe sometimes in the appendix section they'll tell you. $11 million parameter ResNet 18. Oh, this is just for classifying the data set. Okay. They're using a TPU v2 for the... What? Why are they using two different types of TPUs? What is going on, guys? What is going on? Here you go. So the 256 TPUs, that was really only the biggest version of this. So you see, this is their biggest training run right here, a 2.7 billion parameter model for 16 days on 256 TPU v3s. Dude. The Genie arch diagram. Right here? Right here? ST transformer. The entire lamb is discarded. We utilize our ST transformer, the causal mask, blah, blah. They don't. Yeah, I don't think they pre-trained. I think they, because it's like their own custom model too, they just trained it from scratch. Okay. All right, guys. I think we might end it there. Let me take a big sip of water. I'll do some quick summarization here, and then I'll give you guys back some time. Question by Mina Jewel. What's happening here? You're perfect. Perfect timing, man, because I'm just about to summarize what we did today, and then we're going to end the stream. So today, the stream was called Diffusion Game Engine, and we were reviewing this latest paper here called Diffusion Models are Real-Time Game Engines, published by Google this week. This paper has gotten a bunch of excitement. A bunch of people have been publishing videos and talking about it. You got Jim Fan talking about it. So we figured we'd do a little deep dive, go into the paper, see what's going on. And it's a world model paper. So a world model paper, there's a couple other ones that have come out. You have Genie here, which we read on the channel, which is also a Google DeepMind world model paper. And then you have the OG world model paper from Schmid-Huber, published in 2018. And after reading it, I actually think it's not as good as these two. So I think these two world model papers, Genie and the original one, are better than this one here. This one actually isn't particularly impressive because they don't really do very much here, right? So basically what they do is they collect a data set of 900 million frames and actions from Doom, and then they take a pre-trained Stable Diffusion 1.4 model and basically overfit it on that such that it can predict the next frame of Doom. So they get a diffusion model that can output frames of Doom given a sequence of frame action pairs of a currently playing Doom game, right? Which is kind of cool because you can play this, right? So you can kind of like, you can sit there and click keys, and each key that you click is an action, and every time you click that action, you can then feed that along with all the previous frames into this diffusion model, and it'll give you the next frame. And it does it fast enough because of the 4-step diffusion model, right? So diffusion models can be kind of slow because they have to iteratively denoise. This one, they do it in 4 steps, and they even distill a version that has a 1-step denoiser, but ultimately they can get roughly 20 frames per second. But that's pretty much it. Like, they don't really do much else. They don't try to get a reinforcement learning agent to play this game, which I think was the coolest part of the original world model paper, was that you were able to get, you were able to train a reinforcement learning agent in the dream directly, right? So like the whole argument of the world model paper was that, hey, rather than learning directly in the pixel space of the video game, which is expensive, we can train a world model, which effectively kind of compresses the video game into this little latent Z space, and then we can play in that and learn in that little latent Z space, and it's significantly cheaper and faster to learn RL in that, which was kind of the dream of this paper, right? It was kind of the goal. In this paper, they had the cool part where they basically create this latent action model that can learn the action space of kind of arbitrary sequences of frames, right? So they can basically take a data set of robot trajectories and kind of learn, disentangle the different actions that are possible in this robot. But in this one, they don't really do any of that. The actions are just hard-coded Doom actions that get embedded. The RL agent doesn't get used for anything other than just generating this giant data set. And then the model, the world model that they have, is significantly bigger than the game of Doom itself, right? So the Stable Diffusion is multiple gigabytes versus the game of Doom is like 2 megabytes. So, yeah. That's pretty much it, guys. You know, full game state, kind of overfit to shit, but whoever figured out their social media kind of advertising campaign, really stellar work there, because everybody was obsessed with it, you know? That's pretty much the paper. Pretty cool. World models continue to improve, and people continue to make the world models, and I think that really where is this all going is going to basically, you're going to have these world models that are used to train reinforcement learning agents like the Optimus robot, like your autonomous vehicles. And then you're also going to have world models that are being used to effectively generate video games. So will video games of the future actually use like a game engine like Unity or Unreal that's actually calculating physics and actually calculating the lighting? Probably not. It'll probably be some deep learning model that you input actions into and it just outputs frames. But I don't think that deep learning model will just be trained from a data set of the game already, right? That kind of seems like you use an egg to create a chicken to give you eggs. Like it doesn't really make sense, because here you already have the game in order to do that. But that's just my opinion, you know? I'm sorry if you're one of these guys. Hope you guys got something out of that. Thanks, Fabula M24, Minhajul, Yatharth Hijups, little Kirby face, Sheb, Frigo, Chicken P, Abinaw. Who else? Splinter Seller, Aries, Ogum the Bad, Pedro Santos, Sarah, Rawal, 770, Jeff, Diego, Snooks, Ed, JJ Sheep, Cigar, and Khalil. Thanks for watching. Hope you guys got something out of that, and see you guys next week.